Hey guys, so we're going to keep on moving along in chapter 11. Today we're going to look at 11.4. We're going to start talking about polyhedrons. The first page of your notes is a bunch of vocabulary, and just to save time, I'm not going to write this all up on the whiteboard, but you can open up my answer key and copy from my answer key, but I am going to talk about each of the terms, okay? So a polyhedron, okay, if you look at the notes, it says a polyhedron is a solid that is bounded by polygons. And in your notes, there are some examples of what polyhedrons are and are not. Okay, so we have pyramids and prisms. Those are polyhedrons. And then non-polyhedrons would be cylinders, cones, and spheres. All right, polyhedron, again, by definition, it's a solid bounded by polygons. So your prism, all right, this one here, rectangular prism, has a bunch of rectangles as all of the surfaces. Our pyramid has a rectangular base, a quadrilateral as the base, and then triangles as the sides. So those are polygons that form our polyhedrons. Over here, a circle is not a polygon. The cone has a circle base. Cylinder has circle bases as well, so those are not polyhedrons, okay? So to talk about each of the terms, I'm going to show a polyhedron. Since I don't have my actual geometric figures here at home, I had to just grab a box of pasta to represent a rectangular prism. All right, so one of the terms is a face. A face is a flat surface of the polyhedron. So this front rectangle would be a face. The top rectangle will be a face. The bottom rectangle will be a face. All the different surfaces of this rectangular prism are faces, okay? The edges. So where two faces meet along right here, this would be an edge. The definition is a line segment formed by the intersection of two faces of a polyhedron. Okay, so I have an edge here where the two faces meet, an edge here, an edge down here, and so on and so forth. The vertex, a point of a polyhedron where three or more edges meet. So the corners, those are your vertices of your polyhedron. All right, this corner here, this vertex here is the intersection of the front face, the top face, and the side face. Next, we have a cross section, and I'm going to have to show you the examples in the notes for this. The cross section is the intersection of a plane and a solid. Let me show you. On page 19 in your notes are some good examples of cross sections. So if you look, we have here, sorry, I can't read backwards. Here we have a pyramid, and we have a horizontal plane intersecting the pyramid. The horizontal plane is parallel to the base, which is a four-sided figure quadrilateral. We'll call it a square. I have square in parentheses because I'm not 100% sure if it's a square. So the cross section will be a square. The cross section face is going to match the plane that it runs parallel to. All right, here we have a vertical plane, and the vertical plane is going to run parallel or match the vertical lateral faces, which are triangles. So we have a triangular cross section, okay? So that's what a cross section is. Solid revolution, a three-dimensional figure that is formed by rotating a two-dimensional figure around an axis, and I'll hold my notes up to show you that as well. And then the axis of revolution is the line at which the two-dimensional figure is rotating to form the three-dimensional figure. So here we have a two-dimensional rectangle. If we rotate that rectangle around that vertical axis, if you rotate it around, what you're going to form is a cylinder, which becomes a three-dimensional figure. All right, and then the diagram's the same because this time we're just talking about that line that we're rotating about. That is your axis of rotation. Okay. All right, so that is all the vocabulary. Next, you're going to be looking at the notes, and I'm going to kind of skip over some of the problems that are very straightforward and easy, such as counting the faces, counting the edges, and counting the vertices. I'm pretty confident that you guys can look at a figure and count the edges, the vertices, and the the faces. I am going to just draw up one quick diagram so that I can explain to you Euler's formula. Okay? At least I'm going to try to draw this figure. All right, so the very first problem in your notes, it says F, E, and B, faces, edges, and vertices. And we have pentagonal prism. So pentagon has the bases. Again, I'm not great at drawing three-dimensionally, so I just draw two pentagons, and then I try to match up the vertices that match, and then I'll go back through and try to make things look more three-dimensional. Let's go over here a little bit. All right, so we'll do this one. We'll do this one. We'll do this one. So 1, 2, 3, 4. Okay, I think that's good, right? Yeah. All right, so did my best. There's our pentagonal prism. Has pentagons as the bases. That's how we name prisms. We look at the shape of the bases. Since the bases are pentagons, we call it a pentagonal prism. If the bases were triangles, it would be a triangular prism. If the bases were squares, it would be a square prism, which is a cube. If it was rectangle bases, we call it a rectangular prism, and so forth. So what you're going to do is count the faces, count the edges, count the vertices, and then I'm going to explain Euler's formula. So as far as faces, we have the two pentagons, right? And then we have all of the rectangles that connect the two pentagons. So you have two polygons, and then 3, 4, 5, 6, 7 faces. Edges. You have the 5 edges of this pentagon and the 5 edges of the back pentagon, so it's 10. And then all 5 segments that connect the 5 corners. So that's 15 edges. And then the corners, the vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So again, I'm not going to do problems 2 and 3 where you're doing the same thing, but I am going to explain to you Euler's formula. So Euler's formula is faces minus edges plus, faces minus edges, vertices, I'm saying faces and writing V. Vertices minus edges plus faces equals 2. There we go. I'm going to say that again since I messed up a bunch of times. Vertices minus edges plus faces equals 2. So to verify Euler's formula, all you're going to do is plug in these values and make sure that it works, that it's correct. So the vertices is 10 minus the 15 plus the 7. And we're going to check to see does that equal 2. So 10 minus 15 is negative 5. And then negative 5 plus 7 is 2. So it works. So if you're asked to verify Euler's formula, this is Euler's formula. You're going to substitute in the vertices, the edges, and the faces, and make sure that it works, okay? If it doesn't work, go back and double check that you counted correctly when you're counting the edges, the vertices, and the faces, okay? All right. Let me erase. So again, you can look at problems 2 and 3, maybe try them on your own, and then compare to my answer key to make sure you're okay. Drawing a net for a polyhedron, and then again, it says verify Euler's formula for the net. To draw the net, you basically want to flatten the figure. All right, so I'm going to look at number 3 for this one. Oh, that's not a good one. Number 3. So for number 3, if you look at the figure, the base, it looks like is a 1, 2, 3, 4, 5, 6, 7, 8-sided octagon. So it looks like we have an octagon. Oh, that's not an octagon. Oh, back up. All right, so there's your octagon. And then we have this point up here that they all meet at. Again, I'm not the best at drawing three-dimensionally, but you get the idea, okay? So this is our bases. This is our octagon. What you want to do is you want to flatten, like kind of think of it as opening up, dropping all of the triangles down. So what would that look like? So again, you have your octagon. And then along each of the sides, if you drop the triangles down, there's one triangular side, another, right? You should have 8 triangular sides. Right? If I was to close them all back up and pin them all back up to the top, you would have your triangular prism. So that would be the net, not drawn to scale, obviously, but that would be the net for the figure. Okay, so that's problem 2. All right, moving along. So for the next section, it says use Euler's formula to fill in the missing values for each polyhedron. So again, I'll write down Euler's formula for you again. It's vertices minus edges plus faces equals 2. So for example, I'll do number 5 because they're all basically the exact same. So for 5, you don't know the faces, you know the edges is 24, and the vertices is 16. So basically, we're just solving for the faces using the formula. So if the formula is V minus E plus F equals 2, fill in what you know. Vertices is 16. Edges is 24. I don't know faces. It equals 2. And then you're going to work through the algebra. All right, so 16 minus 24 is negative 8 plus F equals 2. Add E to both sides, and you're going to have 10 faces. Okay, so this figure has 10 faces, 24 edges, and 16 vertices. Okay, so that's what you do for problems 4 through 7. For problems 10, 11, and 12, this is where you have to describe the cross section. Again, the cross section is going to run parallel to the base. Or it's going to be the same shape as the base that it runs parallel to, or face that it runs parallel to. Riley, watch your steps. Sorry, guys. All right. So, for problems 10, 11, and 12, I again want you to see if you can... Sorry, my daughter is, for some reason, not leaving me alone. Thank you. Go away. Get this all set up. Okay. For 10, 11, 12, I want you to look at the figures and try to decide what shape the cross sections would be. And then check your answer using the notes, using the answer key. If the plane is running horizontally, look for the horizontal face that it looks like it's running parallel to. The cross section should be the same shape. Okay. And that is it for, I do want you to look at page 19 as well. Look at problems 5 and 6. Okay. These I want you to try on your own and then compare to my answer key. Look to see what kind of shape you think would be formed, what three-dimensional shape you think would be formed if the two-dimensional shape was rotated about the axis. So just take a look at those. Don't stress out too much about them. I just want you to think to see if you visually could think what shape it would be. Okay, and check your answers in comparison to what I have in the notes. All right, and then you'll jump online and do the homework. If you're having trouble as you're working through the homework, feel free to send me an email and I can try to help you through the problems. All right, see you later. Bye.